Right, so in our Matter and Interactions book, 4th edition, we're going to be looking at problem 30 in chapter 3. This problem is going to be dealing with the gravitational force as far as using the momentum and the position update principles. Alright, so we're mostly going to be focusing on problem A and C. Problem A is asking, at time 1 times 10 to the 5th, what is the momentum for the first star? And problem C is asking, at time 1 to the 10/5, what is the change, or the new position for the first star? Alright, so to start us off, the first thing you're going to notice is that our final momentum, the formula for that is equal to the initial momentum plus the total force put on said star times the change in time. We already know the change in time is 1.10 to the 5th, so that's one variable knocked out the way. The other, our initial momentum, is going to be equal to our mass times the velocity of the first star. And through calculations, you can see that's going to be, in vector form of course, 2.8 times 10 to the 35th, 2.4 times 10 to the 35th, and negative 3.2 times 10 to the 35th. Alright, next up, our last variable we need to find is our F net. In this case, it's just going to be gravity. It says there's no other forces acting on it. So here's the formula for gravity: negative g times mass 1 times mass 2 divided by the magnitude of the distance between the stars squared times the unit vector r. And in this case, g is a constant 6.67 times 10 to the negative 11th. We're going to multiply that by our two masses. We have all the information up here. The star 1's information, mass 1 is 4 times 10 to the 30th. And star 2, mass is 3 times 10 to the 30th. So we're going to multiply those together and divide those by the magnitude of the distance between, which I do have those all defined right here as well. The distance in r itself is 3 times 10 to the 10th, 6 times 10 to the 10th, and negative 5 times 10 to the 10th. The magnitude is 8.37 times 10 to the 10th. And the unit vector is 0.358, 0.717, and negative 0.597. Right, so here we go. The 7.006 is going to be when you square that magnitude times our unit vector, of course, and when you multiply all that out, it's going to come to the 4.088 times 10 to the 28th, 8.188 times 10 to the 28th, and negative 6.818 times 10 to the 28th. Alright, and putting it back into the formula, we're going to have to add that first momentum times the net force times delta t. And when plugging all that in, here's your final answer. The final momentum is going to be 2.841 times 10 to the 35, 2.482 times 10 to the 35, and negative 3.268 times 10 to the 35 kilograms per meters per second. Alright, and problem C is asking, at time 1 times 10 to the 5th, what is the final position for S1? To find that, here's the formula. The final position is going to be equal to the initial position plus the average velocity times delta t, which is the change in time. So we're assuming the velocity is constant here, so we're just going to use the velocity we were given for star 1, the 7 times 10 to the 4th, 6 times 10 to the 4th, negative 8 times 10 to the 4th, meters per second, of course. And plugging all in what we already know, we know delta t is the 1 times 10 to the 5th as given, and our initial position was also given. We're just going to plug everything in right here, and the final answer is going to be 2.007 times 10 to the 12th, negative 4.994 times 10 to the 12th, and 3.992 times 10 to the 12th.